and then move into chapter 4 and discuss that a little bit, and then we'll see where we get. Maybe start to address what's going on in chapter 5, but I kind of doubt that. So where we missed in chapter 2 was looking at temperature. It's something that we've consistently seen everywhere else. I mean, every day we think about it in Arizona, at least during the summer. So there's different scales on which we can report the temperature. And really kind of coming up with a definition on what temperature is a bit difficult, because it's not something that we can really touch or control all that well. But we did happen to note that certain liquids respond oddly when the temperature is changed in closed systems. What I mean by closed systems, we look at a thermometer. So our standard is typically mercury, because mercury has very predictable changes in its properties with changing temperature. Mercury is also toxic, which is why most thermometers now are measured with alcohol instead of mercury. The problem with alcohol is they aren't quite as accurate. So they degrade over time and you get other issues with them as well. Okay? Ultimately, what it's trying to measure when we're looking at a temperature is the average kinetic energy within an individual sample. Okay? Which again is kind of a confusing thing, because when you look at units of energy, we're considering typically joules or calories. We don't look at temperature as a measure of energy. So it's kind of an odd relationship. There are 3 temperature scales. If we're American, we deal with the Fahrenheit scale. I think everywhere else deals with Celsius. Is that right? Yeah. Probably. The Celsius scale is typically more widely used. Here in the U.S., for some reason, we've stuck with the Fahrenheit scale. Okay, there's probably some history, and again, probably some crotchety old guy complaining about it. And that's why we have Fahrenheit. We have then a third scale, and that's going to be your Kelvin temperature scale. When it comes to most science applications, a lot of them are in kelvins. And the reason we pick Kelvin is because it's the absolute temperature scale. Okay. One of the even nicer reasons we use that, so what does that absolute mean? What are your possible temperatures with Kelvin, or even Celsius for that matter? So Celsius, what happens if we get really, really bitterly cold? What happens to the temperature? Goes negative. Okay. What's the problem with negative signs when we deal with mathematics? That negative sign starts to confuse our mathematics and makes life difficult. What happens when we get bitterly cold in Kelvin? It's still a positive number. It's just a smaller positive number. So Kelvin is nice in that we don't have that negative sign issue. Okay, so it simplifies a lot of our mathematics, and we'll end up using it fairly frequently in the rest of our calculations, both this semester and if you take future chemistry classes. The degree Celsius does poke its head up in a few different applications, and those are typically applications where it was discovered or it was needed to have a measure of temperature well before we came up with standardized units as far as kelvins go. Okay, so we'll look at one of those applications where we see Celsius show up in a calculation. Yeah, Kylie.
Why do they not use the degree symbol on Kelvin?
That's a good question. I don't know. Yeah, sorry.
It's driving me crazy.
Does anybody know? Okay, the degree symbol actually stands for the person who originally discovered it. So it's a superscript degree for original. So it's original Fahrenheit, original Celsius. But since Kelvin was developed much later, it didn't have an original discovery with it. We just applied it from something else. Does that work?
Yeah.
Okay. I did just make that up.
What about I was doing the post lab stuff, and it was easy to go from Celsius to Kelvin.
Yes.
But to get Fahrenheit,
Ridiculously
Celsius
easy.
and then Kelvin.
Yeah, so what we'll look at here, maybe here on the next slide. Whoops. Oh yeah, there it goes. Not quite the next slide. We'll evaluate some of important points first, but we will go back and look at your conversions in a second. And you're right, it is a pain to deal with anything in Fahrenheit. whereas the Celsius to Kelvin scale is a much easier one to transition from.
It says when units are absolute or measured directly with respect to something else, one drops degrees from the units. Of course, this is someone's best answer.
Yeah, that's, I don't know, I like my original.
I started typing that.
Huh. So there you go. Allegedly, when it's an absolute scale, the degrees disappears for anything that you measure. So, seems interesting. I don't know. Okay. Common temperature ranges to evaluate. We almost always set everything up to water. Why water? Why is everything standard off of water? It's the most prolific substance on the planet. Okay, we're looking and easily transitionable between the phases. So when we're looking at trying to come up with some standardized scale, a lot of things go back to water because we have a lot of that. And we can transition fairly easily between those individual phases. So it's kind of a nice thing to use. So when we look at Fahrenheit, when you freeze, you're at negative 32 degrees Fahrenheit. And it boils at 212 degrees Fahrenheit. How many people knew those numbers, out of curiosity? Okay. Both of them, or just the 32? Okay. So to me, I don't remember the boiling one. That always takes me some time to actually figure out. When we go to Celsius, anybody know your Celsius, freeze and boiling? For some reason, even though we're working in the Fahrenheit scale in the States, almost everybody knows your Celsius freeze and boils, but don't know the Fahrenheit. Seems very odd to me, but it's just the way it works. So when we're looking at Celsius, our freezing point is 0 degrees Celsius, and our boiling point is 100 degrees Celsius. Okay? When we move to Kelvin, now the numbers seem to make even less sense. But the reason dash is a really bad thing to show in there. Let's make that a colon real quickly so we don't get confused. That's not a negative. Yeah, I can go through and adjust that with all of those. Those are colons, not dashes. At least for these. Yeah. Okay. So in Kelvin, our water freezes at 273 Kelvin. You notice I put in the degree. Oh well, probably a copy paste. And boils at 373 Kelvin. Okay? So those are some common leverage points between these. If we now want to try and convert between our individual units, that's where things can get a little bit trickier, particularly when you're dealing with anything in Fahrenheit. And what do I mean by that? Well, let's compare our Celsius to Kelvin. What's the relationship between 0 and 273? 273. What's the relationship between 100 and 373? 273. There's a nice, easy relationship. What's the relationship between 32 and 0? Maybe 32. How about 212 and 100? That's not 32. Okay. There are ways that you can derive that conversion factor. I will tell you right now, I don't remember them because I think Fahrenheit's pretty useless. Okay? For that major reason, I'm not going to expect you to memorize the Celsius and Fahrenheit ones. Let's actually write that as a different thing. Let's make it positive. I will provide these on the exam. Okay. However, I will not provide the Celsius to Kelvin. I do expect you to have that one memorized. You'll notice I carried it out to a couple extra decimal places. That's just because there's a few numbers for some reason I happen to remember. This happens to be one of them. I happen to remember that it goes 273.15. All you really need is the 273. Okay, why just 273? Sig figs. Most of your calculations involve 3 significant digits. If we go through and take a look at our Celsius and Kelvin, 273 is usually enough for our sig figs. Okay? When dealing with our Celsius and Fahrenheit, those 9/5, particularly if you look at the lab manual, are represented as something else. What do they actually use for those numbers? They use 180 over 100. That is your official relationship, that 180 over 100. Okay, as an interesting observation, when we looked at 0 degrees Celsius to Fahrenheit, what was our relationship? Said it was 32 degrees. What's 180 plus 32? 212. What was the boiling point for water? 212. So we can, if you wanted to, go through and derive this relationship, entirely up to you. Okay, what I expect you to be able to do is to use these to go through and do your conversions between your Celsius and Fahrenheit. Okay? Yes?
The bottom one says add 273, and then an example says 273.15.
Oh, you're saying here?
Yeah.
That's what I was saying. 273 is the one you're responsible for? Sorry, I just spit on you. Maybe I shouldn't have told you. 273 is what you're responsible for. The 0.15 just happens to be a random number that I remembered that is associated with that.
Oh, okay.
All right. So it is more accurate to represent it as 273.15. Okay. Other questions on these? Okay, I think maybe we've got some conversions here, so let's go through and figure some of these out. Body temperature is 98.6 degrees Fahrenheit. What is body temperature in degrees Celsius? And then in Kelvin. So if we're going to go through and try and do this conversion, we need to decide what our answer needs to be. Bless you. So what do we know about our answer? Set it up just like we've done everything else. Equals what? We want to go with degrees Celsius. Needs to be our answer. How do we get to degrees Celsius? Which formula do we use? Blue or red? Red, because red's the one with the degrees Celsius on it as our answer. It says to start with our degrees Fahrenheit, so 98.6 minus 32 times 9 over 5. I have intentionally written it out like this. Those of you that have taken mathematics or some more strict mathematics classes might be cringing right now. What's the problem with how I've got this written? If you enter it into the calculator like this, what you are going to calculate is not the quantity 98.6 minus 32 times 9 over 5. You're going to calculate 32 times 9 divided by 5, and then subtract that number from 98.6. Okay? There's a very big reason that those parentheses were in there. Okay? You have to do your addition subtraction first, then do your multiplication division. If you don't, you're going to end up swapping and getting the wrong answer when you finalize it.
Don't you have your 9 fits backwards?
No, I put it up. At least my formula says I did it right. Oh, dude, I copied my formula wrong.
Because that's 120. That would be a really hot person.
Man, yep, I copied the formula wrong. Here we go. So let's fix our equation here. By the way,
Did you get 120?
just in my sort of self-defense on this, the textbook slides that I pulled were also wrong. I looked at it and was like, that can't be possibly right. So I tried to fix it, and apparently I bombed that. So our 9/5, if we're going to convert across for our Fahrenheit degrees Celsius, needs to be 5/9. Okay.
He got it. He somehow got it your way. That's not possible.
Well, maybe you're dividing. Maybe he's dividing so it switches.
Well, I use parentheses, so it shouldn't matter.
Your temperature should come out at 37, yeah, 5/9.
But he did it in his. He used 5/9 or 9 fifths.
But he divided by it, so it flips it. It is 5/9. I want to be clear on that. It is 5/9 for our Fahrenheit.
Not for Celsius.
Okay. The top one needs to be 9/5. You can algebraically shift one formula over to the other. Okay, so let's verify this. Let's assume our top one is correct, because I'm like 90% certain that one's right. We can convert that over into our Fahrenheit formula by shifting our information around. So what we'll do is subtract 32 from both sides. And we would end up with, so let's just cross all that out for the moment. 9 over 5 times degrees Celsius equals Fahrenheit minus 32. Multiply both sides by 5, divide by 9. We get degrees Celsius equals 5/9 times Fahrenheit minus 32. You memorize one equation, you can algebraically shift it into the other.
So wait, for the Celsius one, it's not plus 32, it's minus 32.
It is minus 32. Or let's try again. Top or bottom? What are you referring to, Troy?
The first one?
The first one is plus. To get the 32 to the other side, what do we have to do?
Oh, okay.
You have to subtract. No. So here we go. Let's clear all that and go to this one. Here's your formulas. This is not, oh, I did the next slide. This is not 9/5. This is 5/9. Okay, let's work the problem. 98.6 degrees Fahrenheit minus 32 times 9/5. I keep doing that. 5/9 gives us our degrees Celsius at what temperature? 37 degrees Celsius. Okay, that is your proper body temperature as far as degrees Celsius goes. That just happened to again be a number that I've got memorized. Is that the correct answer? Would you be correct on the multiple choice? You'd be wrong. What's the issue with it? Sig figs. We'd go through and evaluate our 5/9. Those are exact numbers, so they have infinite significant figures. What's going on with that 32? When we're dealing with this conversion, there's a couple ways that we can approach it. We're moving from English to metric effectively. When we do our English to metric conversions, how many sig figs do we carry? 3. So even though it's written as 32 with just 2 sig figs, by standard notation, that has 3 sig figs. If we move to our next starting temperature, how many sig figs? 3, which means our answer needs to be reported as 37.0 degrees Celsius. Count for the sig figs. Yes?
So just to make sure, 32 is because it's a measurement, so it's not.
Because it's an English to metric conversion. In our English to metric conversions, we keep it at 3. Okay? Other questions on our conversions? I promise that if on the test I give you the wrong conversion factor, I'll give you a free 5 points. Okay? I don't know, we'll see. Okay? I will also go through and post an announcement clarifying that, and I'll try and edit the slides and repost the slides so that that's fixed permanently. The next aspect to evaluate is looking at heat. So temperature measures our average energy of our particles within the system. Heat is a measure of the total energy. Okay, so heat and temperature are related. It's kind of difficult to see that difference until we actually look at an example. So if we took these 2 beakers, one of them had, 500 milliliters of water and 1,000 milliliters of water. The one that's going to cause more damage is going to be the one with 1,000 milliliters, because even though it has the same temperature, there's more of it to translate that temperature across. Okay? That more energy is your heat value. Okay? So heat takes into consideration the mass of the substance as well as the temperature. Temperature doesn't care about how much it is, it just cares what the actual average value is. Okay? So they're related to each other, but not the same. When we look at heat, heat carries slightly different units, because remember, it's representing something slightly different than temperature. What it's going to represent is the energy within it. Energy is typically expressed in either joules or calories. Joules seems to be, to me at least, kind of your standard energy unit for all forms of energy. Calories comes in typically when we're looking at temperature-involved substances. Okay, so when we're looking at heat, that's typically where you see calories appear. These two units are different from each other, and you have to be able to convert between them because they represent slightly different relationships. Yes?
Is it true that calories, when you look at nutrition, it's actually 3,000? Like when?
I'm not positive on that, but I think it is the case. Yeah. So if you take a look at your nutrition packets, when they record those as calories, I'm first off almost 90% certain it's not the same calorie. And then second off, I don't know the exact relationship. Do you know it?
From the reading, nutritional calorie is a capital C cal.
Yeah.
And 1 capital C cal is equal to 1 kilo cal.
There you go. So there's your relationship. So isn't that fun? We get calorie here, but we also have, ready for this? Calorie. Are they the same thing? No. All because it's capital versus lowercase. Don't blame me. I didn't invent it. I think that's stupid. Okay? So be aware of that when you're looking at different relationships. Watch out for those. I will try my best to not incorporate having to convert those two relationships unless I directly tell you that's what's going to be happening. Okay? Specific heat. So specific heat is now looking at a very interesting property of an individual material. What it's going to refer to is the amount of heat or our energy necessary to cause 1 gram of that substance to go up by 1 degree Celsius. So it's kind of a similar idea as density, where we're relating the mass of a substance to its volume that it occupies. Except here we're now looking at how the heat is related to that substance. Okay, so you end up with this relationship, or that energy per gram degree Celsius. Depending on which energy unit you choose, your number changes. Okay? So if we're going to try and convert calories into joules, the relationship happens to be 1 calorie equals 4.186 joules. Okay? How could we figure that out? Well, if this is the exact same substance, what happens if I multiply both sides by grams? Grams will cancel in the denominator, right? What happens if I multiply both sides by degrees Celsius? Also cancels. So how do we figure out our conversion factor between calories and joules? We just did it. All we got to do is get rid of the like units. Okay? Depending on who you talk to, you're going to, again, get slightly different unit preferences. I personally would choose joules over calories. It seems to me that your textbook really preferences the calories over joules. Okay? And that's just because of probably our backgrounds. I tend to be more in the physical chemistry aspect. When we shift into physical chemistry, we're concerned about joules, so we don't have to convert to calories or calories to joules. In this case, they're looking at it as probably one specific problem, in most cases probably related to water or to nutrition, in which case the calorie unit seems to make a little bit more sense. So it just depends on the different applications that you're working at. All right? What interpretation can we do from this? So the first one, we have a conversion factor, which means we can now convert mass, degrees Celsius, and calories, or relate all of those to each other within an individual problem. Just like we could relate mass and volume to each other if we had an individual species to go through, okay, if we had that density. So we get those problems, but we also get one extra piece. We want to know something about the size of that number. Okay, so what does it mean if we have a big specific heat? I think you can cheat. I think I wrote it up there. If we have a big specific heat, that means I have to put in a larger amount of energy to cause the temperature to go up by a degree. What does that mean? That species can absorb a lot of heat. Okay? What does that mean as far as its insulating versus conducting abilities? Any ideas? Should it insulate? Would it act as an insulator or a conductor of heat? Okay, if we take that substance, put a blowtorch to it, we're adding that heat into it, and we put our hand next to it. Okay, if it conducts heat, what happens? You feel it right away. The heat's directly translated through the material. What does that mean happens to the temperature? Temperature goes up very, very, very fast. So if I can dump in a ton of heat into it and the temperature does not go up, it's not conducting the material. It's an insulator. So the larger our number is, the more of an insulator. The smaller that number, the more of a conductor. So in general, what would we predict, say, for something like gold or silver? High specific heat or low specific heat? Relatively low. Let's pick an easier one that maybe you've worked with, say copper. What do you think about copper? Where's the most common use for copper in our everyday life? What was that? Wiring. Oh, that's true too. But wires, looking at electricity. Anybody seen really expensive pots? What are they typically made out of? Copper. Why? Because copper quickly and efficiently conducts the heat through the material. So that if you put a copper pot on the stove, the heat from your stove goes up and fills the entire pot, which means you cook evenly. You don't get brown spots or burn spots in different parts of the pan because it conducts that heat very well. So as far as its specific heat, what should it be, high or low? Low, because it's going to conduct that heat quickly. So here's a possible exam question, which would have been a lot cooler had we gone through this slide before the last exam. Okay, which of the following substances is expected to have the largest specific heat? Ooh, interesting. This is actually going to require you to pull on a couple different concepts. So what species would have a large specific heat? Any guesses? So we got copper, okay, silver, gold, platinum. Okay, we'll stick with copper and gold. We said those two conduct heat. What am I asking as an extra part of this question? Metal or non-metal? If you remember back to your properties for metals and nonmetals, which one can conduct heat? Metals. Which one does not? Nonmetals. So we can go back to this list and say which of these is a nonmetal. Where's calcium? Metal. What's our answer? Carbon. Okay? So if we go through and take a look at that, we would expect carbon to have the highest specific heat because it's the non-metal in this list. There's no guarantee. This is an approximation. Okay? If I'd given you another metal on this list, let's say instead of carbon, we went through and said gold. How would you figure it out now? Turns out it's not that easy. Okay? Each of those materials has slightly different specific heats. I went through and made sure that when I asked this question that carbon did come out with the highest one. But between those, in between, right? The specific heats between a lot of those metals is very non-periodic as far as our trends go. Okay? So evaluate your definitions, metal, non-metal, and apply that back to our specific heat, because we know our metals conduct heat. Okay, questions about that? What was another aspect of this question that you were also tested on? So it tests you on metal, non-metal, tests you on specific heat, and it tests you on knowledge of the elements. Okay, so this is a pretty brutal question because it asks a lot of different things. As we progress through the semester, you're going to end up having questions that are going to ask multiple or have multiple pieces to them that you need to be able to answer the question appropriately. Whereas with our first exam, it was really straightforward. There was only one thing being tested on. Very rarely did you have more than one. Okay? So now we can move into chapter 4. I did post an announcement with all this homework on it. Like I said, we're going to shift through chapter 4, then jump to chapter 5 a little bit, and then go back to chapter 4. Okay, so we're doing a lot of back and forth with this. With chapter 4, what we're going to talk about first is primarily some kind of history. So again, it's my history, and of course my history is questionable, but for the most part it's roughly correct. Then we'll shift to chapter 5, which the beginning of chapter 5 requires some understanding of what happened in chapter 4. And then we'll go back to chapter 4 to look at everybody's favorite, ask any chemist you want, everybody loves quantum mechanics. That's chapter 4, okay, the end of chapter 4. Okay? That was sarcasm. Very few people actually like quantum mechanics. Okay? So, like I said, it's already posted online on Canvas on an announcement, so you've got access to those, and maybe even a few more homework questions as well. Oh, I guess in that respect, remember you should finish chapter 2. Finish the chapter 2 homework on the specific heat and temperature if you haven't already. So I noticed when I went through and graded the homework that a lot of people already did that. Other questions? What? You haven't seen that commercial? The Old Spice commercial? YouTube Old Spice commercials, you'll see. It'll make more sense then. Dalton, atomic theory. Yes, question.
Is chapter 4 from this edition as well, or
Chapter 4 from the 7th edition. It's the 5th edition in chapter, or the 5th chapter in edition 6. Right. Dalton was kind of our founder for atomic theory. It's kind of the early 1800s, so we get a little bit of history along with this. So when he came up with certain aspects of his theory. When are we done?
940.
Sorry.
Plenty
I
of
looked
time.
at those hands differently. Summary of our theory. So the first thing he went through and said is that elements are composed of tiny indivisible, that word, indestructible particles called atoms. Okay, so he said everything was made up of an atom, and that was as small as we could get. Is that true?
No.
No. Okay. But remember, this is the early 1800s, like right around the turn of the century. So that's pretty, big thing to go through and say is that everything's made up of the same individual pieces. We're just changing their arrangement. The next thing said that all atoms, or all atoms within an element, have the exact same properties. So we can change it from one place to another, but it's always going to have the same properties. Is that true? That one's a little bit harder. Turns out, no, that's also not true. Okay, we've actually talked about an example. What happens when you take sodium metal and you throw it into water? Kaboom! What happens when you take sodium ion and you ingest it? You don't go kaboom. So sodium ion versus sodium metal, even though they're both the same atom, have different properties. Okay? What changed about them? There were smaller indivisible parts that Dalton hadn't come up with yet. Okay? Those indivisible parts, for those of you that know, happen to be some atomic particles, protons, electrons, and neutrons, which we will talk about. What we've done is change the electrons in an individual atom, and that changes its physical properties, which is why we can ingest sodium metal and not have a problem with it. Or sorry, let's try that again. Ingest sodium ion and not have a problem with it. But if we ingest sodium metal, that's a pretty big issue. Yeah?
Did he say anything about their shape?
No. Shape and bonding really came about with Lewis. And that was after we really understood a little bit more about atomic structure, which he didn't really have at this point. So that really required protons and electrons. We can then go through and look at some of his other rules. Atoms of different elements combine to form different compounds. Okay, that's true. We can take sodium and combine it with other species and generate new species that have different properties. So depending on what we mix it with, we'll get different things. Okay, so these compounds are now mixtures of atoms. One of his other observations is that compounds will contain the atoms in small whole number ratios. This one always seems to confuse and puzzle people, particularly when we go through and look at reactions. What we're evaluating is a piece. An atom is a piece, okay, much like a bicycle tire. If I take 2 bicycle tires and a bike frame, assuming we ignore all the other missing pieces, I can make 1 bike. But what if I have 2.5 tires? Okay. Can I jam that half a tire into my bike? Okay, not really. We're looking at whole number pieces when we kind of put these things together. And then lastly, we can combine them in differing ratios to generate new compounds. For instance, we could take 2 bike frames and 4 tires and then weld them together, and we now have a little quadricycle. Sure, why not? Okay. So it's looking at how we can put these individual pieces together. It just so happened that these pieces we couldn't see, but we could see their end result when we got enough of them together. What I've got on the far right is a couple interesting things. So what we could start with is our compound, which would be our circle and triangles. If we decomposed that, we would then have our pieces, a big old circle and a bunch of tiny little triangles that came off of it. Those tiny little triangles and circles would be our atoms. That sun up at the top would be our compounds, or our compound. We could then arrange these in different formations to get slightly different compounds. The image next to it, okay, if you can read that, I don't think I can. I can read the top. It says elements. Okay, and he's got a list. 1, 2, 3, 4. Does he go in order? Goes up to 11, and then he starts jumping around. What is that list of? All of the elements known at that point, or all of the elements known to Dalton at that point. You'll notice he came up with interesting symbols. Why? Because it's easier to put together symbols than to put together nothing. How easy is it to manipulate his symbols versus our current symbols? Can you imagine looking at 115 different shapes, colors, sizes, and trying to have those memorized as opposed to a sequence of letters? Okay. He then went through and picked particular compounds that he was aware of because he was able to decompose or put those individual compounds together. So, for instance, this compound he put together by taking presumably what is hydrogen, and can't tell if it's that one. Might be that one. Good question. I have no idea what that is actually supposed to be. I don't know what his numbering system is. But he combined those 2 things to make a compound. He could go through and then combine it with something else. And he generates new compounds in each case. Okay? Kind of an odd system. You can think back to the 1800s, or even now, you look at that and go, you must be crazy. How could this possibly, any of these things possibly be true? Well, it turns out that a lot of his theories and assumptions did hold to be true. Really, rules 3 through 5. 1 and 2 wasn't that good of a sign, or that's a bit mean to say that. Didn't have the technology to be able to figure out what was going on with rules 1 and 2. Okay? So we can then go through and start to look at further advances. So this really relied on a big, huge discovery. It's kind of actually impressive how important this single discovery was as far as being able to propagate more information. So Thomson was able to come through, and he was able to find negative electrons and positive protons. Okay, any ideas how he was able to find these charged particles? Okay, what that discovery was, vacuum. The discovery of electrons and protons hinged on the ability to have a vacuum. We had to be able to reduce the pressure within a system so small that we could say there was nothing there. What he was then able to do was then generate a current of electrons and protons. That current of electrons and protons was actually a cathode ray tube. So back at the late 1800s, what we had to do was generate this cathode ray. To get this to work, what he ended up doing was generating an electrical current between our source, or our positive and negative end, I don't know which one's which. And what he would do is charge that really, really high. And what they noticed that all of a sudden they started to see this color change. You could see this beam through the middle of it, and you could even see this fluorescence at the other end. Okay, why did you need a vacuum for this? Okay, you needed a vacuum because if there was anything in there, any gas, that electron beam hits that, stops, goes nowhere. So we don't see that intense color. So it's kind of interesting. To be able to do this experiment, we have to have something that we don't get any impact of electrons. Kind of cool. So what ends up happening, if we fill or get rid of the gas within that, the electron beam can actually jump from one end of the terminal to the other. And that jumping process is where he decided that we have electrons. Okay? And effectively, protons as well, because you needed some counterpoint to those electrons. How could he figure out the charge on these? Well, is there something that has polarity associated with it that we knew about at this point in time? Magnets. Magnets. We can wire up a magnet around the cathode ray tube. What happens? The magnet has a positive and negative end associated with it. What happens to that electron beam? It gets deflected by the magnets, which means that beam had to have been charged. Otherwise, it wouldn't have been deflected. Okay? And because we had such a good vacuum that pulled everything out of it, there weren't any atoms within it to be able to do anything. So what does that mean? There has to be a smaller particle. That's where we get electrons and protons from. Okay? Kind of cool. At least I think it's cool. This discovery then started a whole bunch of other discoveries. Okay? The primary one, or one of the more interesting ones, is radioactivity, which your textbook doesn't address, but we might see at the end of this semester. I'm not sure what the schedule is, but you would definitely see if you move into general chemistry. 152 talks about nuclear radiation, and that really started because of this odd discovery. Okay, why is this happening? Why is there an invisible energy? Can we find another source of invisible energy? Okay. So Thomson, we'll come back to that radioactivity in a second. Thomson went through and said, okay, we've got these negative and positive particles, and now he tried to come up with a theory to express how our atoms were made up. Okay, so what he went through and said, well, we got negative and positive, simplest possible option. We put those negatives and positives all kind of floating in a general pudding, if you will. So that's where you get the Plum pudding. Okay? And that was his overall theory. Why do you think he would say put it into this kind of massive, odd shape where there was no center or no left, no right? Okay? How did we deflect the electrons and protons? How do you manipulate those? With a magnet. What do we have on a magnet? A north side and a south side. What happens when we bring the north side near the north side? It repels. So if we're going to put together a theory, is it possible that I could somehow jam, let's say, all of the negatives into one location? No, because what's going to happen? They're going to repel just like the magnet did. Could I take all of the positive charges and jam them all into one location? Nope. Exact same idea. It's going to repel. So this theory seems to make sense. It represents our understanding of what was going on to this point. Okay, so it's kind of a neat idea on what he was able to put together. Is this model true? No. Okay. Kind of is a stretch. Okay, yes, there's positives and negatives, but that's about as far as it gets. Okay. Again, your textbook didn't quite discuss this. Millikan and Fletcher were able to build an experiment. It's typically reference to Millikan, but Fletcher was somebody that helped him out with this. Took a lot of eyesight and a lot of patience to set up this experiment. Okay. The reason they had to do this experiment was that when we went through and looked at Thomson's model, I think I've even got it further back. he was only able to come up with relative charges of negative and positive. He couldn't tell you what the exact charge was. So there's no units on that. He just says, well, this one's positive by some amount, and this one's negative by some amount. Oh, and taking a step further, whatever it is negative, it's also that counter positive. So he was able to figure out that exact ratio. It's a 1-to-1 of opposite signs. But that was about it. He couldn't tell you what the exact charge was. Okay? So we need to come up with some other experiments to do that. That's where Millikan came in, and you're looking at 1911. He was able to figure out the charge on an electron, okay, which is pretty intense as far as I'm concerned. So he took some oil, and he sprayed that oil into this little entrapped area. So when you spray, you get all these tiny little particles. To make things a little bit easier, he then put on a cover plate, okay, or a filter on that. And that's what they're trying to show here, this nice black line. That little filter, though, has a hole in it. So in theory, he made that hole small enough that when the oil droplets then kind of fell through the sky, only one would make it through that hole. Okay, or maybe one or two, but in theory, a whole lot less than just this massive spray everywhere. Okay. On the other side of that hole, he set up a uniform electric field. Okay, so he set up a massive amount of current in between there. Okay, well, what would that current help do? Well, if that particle was charged, he could then set up the current to counteract gravity pushing down. Just like with a magnet. We can put two magnets and balance them, and they kind of hover above each other. Doing the exact same here with those oil droplets. So they oscillate or control the magnetic, your electronic field to the point where they can get it to hover. They then looked through an eyepiece and looked at the little oil droplet. Okay, the reason they needed to look at it was so that they could approximate its size. They would assume everything was spherical, so they could then determine how massive that oil droplet was. Once they knew the mass and they knew gravity's force, they could determine the counteracting force of the electric field. That counteracting force is due to the electron charge. They could then solve for the electric charge, all by looking at that very tiny little eyepiece. Kind of an ingenious experiment, ridiculously painful. I don't think I would have the patience to do that. But hey, that's why they win prizes and I don't. Okay? So we can look at their electron mass. So he was able to figure out these masses. Sorry, not charge. He could figure out the mass of each of these particles by looking at that counteracting weight. Okay? Rutherford also contributed in his experiment, is really one of the big ones that are talked about. So Rutherford, of course, this is how all science work. Rutherford was the primary investigator, and then he had a bunch of peons known as graduate students. Those peons known as graduate students got to set up the experiment, and then they went to Rutherford and said, hey, look at these cool results. And Rutherford said, oh, that is neat, thank you. Give me a prize. That's how it works. It's an awesome system we've got as far as science goes. That's sarcasm for anybody paying attention. So they were able to obtain these things known as alpha particles. Okay? And so they fired these alpha particles at thin gold foil, and they were using this to try and predict or prove Thomson's initial model of the Plum pudding. Okay? So there's a couple questions that would immediately jump to mind. Number one, what do you think I might have a question about? Might be highlighted as something separate or different in that statement. Alpha particles. What the heck are alpha particles? Alpha particles are radiation, nuclear radiation. Okay? We didn't know what they were, but we had some way to control and make this source of alpha particles. Okay? For this experiment to work, that source of alpha particles must be very, very consistent and very manageable. Where do we get alpha particles from? Radioactive decay. Problem with most radioactive decay processes. Okay, as they decay, you generate a whole bunch of other things that complicate matters. So how are they able to get a consistent source of alpha particles? Sort of started on this love story already. Curie. Madame Curie was the one that discovered or contributed to the discovery of radiation. Why was she looking for radiation? Thomson's cathode ray gun. They saw this invisible energy and said, well, let's find another source of it. So it was largely due to her work trying to understand these invisible energy particles that she was able to isolate different compounds that gave off a consistent radiation pattern. And they were able to isolate and purify it. What's the nice thing with a purified substance? You now have a consistent, reliable source that you can then use in an experiment. Without that consistent, reliable source, no experiment. Okay? Why is this even further interesting? What did Curie do with her invention or her process of discovering this radiation? She gave it up. Okay? Instead of putting massive amounts of patents down and preventing anybody from using that information, she made it widely accessible to people like Rutherford, who could then use that radiation source to find more information. So that's the spiel against patents. Patents tend to constrict the flow of information, not increase it. Okay? So now that we've covered that little spiel, we can go back to our plum pudding model. Okay? So you can decide whatever you want about what they were trying to find. Okay? I might be a little bit of a pessimist here and say Rutherford thought Thomson was an idiot and said your theory sucks. I'm going to come up with an experiment to prove you're wrong. He could very well have said, no, you're a really cool guy. I'm going to come up with an experiment to prove you're right. Okay? Why would I say he's proving he's wrong? Well, in the plum pudding model, if we fire alpha particles at it, those positives and negatives are so small that if we hit it with an alpha particle, which is relatively large and high energy, we're not going to see any deflection. It's going to go straight on through the atom, and we won't see anything. Okay? All of our detective surface will be at the other end, and we won't see anything else. So why do I say he was trying to prove him wrong? Well, if we were trying to prove him right, how much of a detector would we have? Just that tiny little section. Which means when we fire it through, of course, the only thing we're going to see is the particles going straight through. What happens if we instead say, I think maybe you're wrong, and now we encircle the entire system? Because if he's right, that extra little system is irrelevant. Nothing happens out there. If he's wrong, that means there's some center to the nucleus, or some center to the atom. Okay? What was the end result? They looked at that developing film all the way around the sample, and what they noticed is that, yes, most particles, or alpha particles, went straight through. But then there were a few that didn't go straight through. You saw some minor deflection, and you saw some massive deflection, almost going backwards. How could that physically be possible if the particles within, or our subatomic particles within our atom, are that small? It's not possible. So he said, okay, there has to be a different explanation. That different explanation is that we now have a tight, compact, dense nucleus, where we've now jammed a whole bunch of these things together. Okay? That is now dense enough that when the alpha particles come through, they impact that and go, oh, that's way too big, and bounce backwards, or off to the sides, depending on how they hit and impact that. It's kind of a neat observation. Okay? With that, your text or the slides went through and listed off some interesting diameters and shapes of individual atoms. I really wish I could tell you how they came up with those numbers from this experiment. I'm not quite sure I believe that they could, but allegedly that's possible. To give you an idea of scale, because those 10 to the negative numbers are always a pain to deal with, if we take an atom and make it the size of the superdome, our nucleus is the size of a marble sitting in the dead center of that. Okay? So if we take a look at an atom, most of it is open space. But there's a very small section of it that is extremely dense and hard-packed. What's that? There's a lot of empty space around or within an individual atom, yes. There's things that occupy that space, but not enough to generate enough mass. Okay? So kind of neat. You don't have stadium seats in that, by the way. Rutherford also predicted that we must have neutral particles in addition to our protons. Okay, why would he say that? We got two big pieces of evidence that we could rely on in that case. Okay, number one, they could determine the mass of your structure, okay, of an individual atom. They could predict that at this point. They knew the mass of electrons and they knew the mass of protons. So they could go through and add up the mass of electrons and protons within an individual atom and compare it to the mass of what the atom was supposed to be. What did they find? Didn't match. Well, crap. That means there has to be something else present making up that mass. So one of the pieces of evidence that they relied on was a mass difference. Okay? Your textbook, or at least the textbook slides, mention that one as the primary thing. I think we got another option, another big option. Why did Thomson say we had to spread everything out? What was his reasoning? The charges, like charges repel. Well, Rutherford's theory was that we brought in all the protons into a tightly compact space. What happens when we bring those positive charges all near each other? They repel. There has to be something there to prevent that repulsive force. Okay? So he could predict that we have to negate that repulsive, how do you spell negate? Not with a C. Negate? There we go. Repulsive forces. Okay, so that's kind of an interesting observation. We can go through with some of our simple understandings of things and actually start to predict what things could be true and what things aren't. Neutrons were experimentally discovered, so they postulated this first, but then they didn't actually discover them in a live experiment until James Chadwick did it. I didn't spend enough time looking up the dates on that to figure that one out, and your textbook didn't give them either. So interesting observations with that. One of the things they found is the neutron is the size of a proton, so it has the exact same mass, but it has zero charge, which is an interesting piece. Certainly couldn't be positive because that then makes the nucleus even more positive. If it was negative, that could try and explain the opposite charge repulsive forces. Turns out, again, it's neutral, not that negative. Okay, so what we try and do is take the understanding that we've got and slowly build on it. Okay? This beginning to end process started with Dalton in the early 1800s and ended in 1915 with our final, or roughly final, understanding of atomic structure. Okay? So in 115 years, you are expected to learn, or you're expected to learn in, what are we looking at? 3 classes, 75 minutes apiece, 115 years worth of material. Okay? It's a big jump within that. And that's just this, never mind everything else that we're going to learn this semester. Okay? So kind of wrap your head sort of around that, try and get an understanding of what's going on, but please don't get too overwhelmed by it. Okay? So now what we're going to do is take a look at atomic notation. So we've got symbols. We can use those symbols, but if we take a look at our periodic table, there's a whole bunch of extra numbers on there. Those numbers we can use. They have some extra information. Those numbers are referencing our protons, our electrons, and our neutrons. So they're giving us some information about that. So when we write out, or when we look at the periodic table, we need to know what each of those individual things mean. And if we're going to write out our symbol to account for all of that, what does it actually look like? Okay, so we want to come up with a notation. So what we've got is an atomic number and a mass number. Your atomic number represents the number of protons, and in the neutral element, the number of electrons. Okay? We'll come back to neutral a little bit later, but for the most part, what we're looking at here is the number of protons. Okay? That number is written in the lower left-hand side of our symbol, representing our nucleus. On the upper left-hand side, we have the mass number. That mass number, as the name might suggest, represents the mass of your individual particle. Okay, well, what things contribute to the mass? Well, proton for sure is there. What about electrons? Did anybody look at the table to see how big an electron was relative to a proton?
1/1836.
Okay. 1 over, what was it? 1,836. Okay. So an electron is effectively weightless in comparison to a proton. So in most cases, we can ignore its contribution to the weight. So our mass number at this point would just represent protons, except What's that extra particle? Are neutrons. That neutron is also going to contribute to the weight. Remember, it weighs the exact same, relatively, to a proton. It just has no charge. So when we're looking at our mass number, it's the sum of both the protons and the neutrons. Whereas our atomic number just tells us the number of protons. Okay? This is known as atomic notation. If you move into 152 at the end of the semester, you start to look at radiation. I would typically reference this as nuclear notation. Why nuclear? Where does it say anything about electrons? It doesn't. What we're really looking at is whatever made up the nucleus. Well, what things go in the nucleus? Protons and neutrons. Okay, so this notation really helps us to understand everything that's happening in our nucleus. It gives us very little information about the electrons. Okay, and we will add information in on where we can find out information about our electrons a little bit later. Okay? So we've got the overall summary up top. We want to go through and take a look at this example and try and piece together all of the information given to us. So first off, this element is silicon. How do you know that? Si. Good. Did I stepwise this? Hey, look at that. I did. Okay, what's the atomic number? 14. How do we know it's 14? Okay, we could take a look at our symbol notation. 14 in the lower left-hand corner. Where else could we find that 14? Periodic table. Where's our atomic number on our periodic table?
Right top corner.
Looks like it's in the top right corner. Okay, how do you know that? Could just say it's 14 to 14. That works. Some periodic tables will hide or shift that information around, so it's really important to know where to find that number. How would you find that if they've moved stuff? Periodic table is effectively a map. Does every map have the exact same distance on it? We take a map of campus here, and then took a map with that same information on it of the city. How big would the map be? It's going to get a lot bigger, right? We want to keep things relatively manageable. So to figure out that manageability, what do we have to do? We have to look at a key. Is there a key on our periodic table? Dead center on the top. In this case, it even says key. Look at that. Hey, that's cool. I didn't actually see that, just so you know. Okay. And if we take a look at that symbol, we can look around the outside. It tells us our symbol, tells us where the atomic weight is found, and it also tells us where the atomic number is found. In most cases that I've seen, the atomic number is almost always up at the top of your element symbol. I've seen it centered, and now I've seen it shifted to the right. Okay, so be aware that that can shift around on you. Look for the legend. Make sure you know where to find the atomic number. Yes?
And I always thought that the number of protons was literally the same number as the number of neutrons. So if it was 14 protons, it was 14.
No, officially, yes, sort of. Okay. The yes, sort of, comes from as you scale upwards, you're adding more protons into it. So as we move from hydrogen to helium, to get to atomic number 2, we had to add an extra proton. Well, those protons start to repel each other. So what do we have to do? We need to put in our glue, our neutron, to prevent that repulsion. Okay, to do that, we end up adding 2 of them, okay, to match. We then go up to the next one. You'll notice it probably goes up by 3, and then by 4. So your proton-neutron count is usually very, very close. Those numbers are almost exactly 1 for 1. Okay? As soon as you start to get larger and larger, you end up building up more positive repulsion. You have to account for that extra positive repulsion. How do you account for it? You add an extra neutron. And that neutron will separate or prevent that repulsive force. Okay? So if you looked at stability for an individual element, you would see that it's close at the lower ends. It's usually 1 for 1. At the upper ends, it starts to get higher. You start to see more neutrons than you see protons. Okay, so it depends. It's not always 1 for 1. We'll come up with another example for why it's not 1 for 1 in a second. We did answer that, right? You already answered that? Okay, 14 protons. What about the mass number? What's our mass number? In this case, it's 29. Here's the point that I kind of wanted to get to, make sure I can see it. Yes. What is the mass number reported on the periodic table? Interesting. The numbers don't match. Why do the numbers not match? Nope. It's a different weight. Why is the weight different? Neutrons are different. So your neutron count can change. Does that change the element? The element still is silicon, but it changes its mass differently. Okay? What we'd be looking at is what's known as an isotope. You said 40, right? Yeah, I doubt we'll get there, but we'll see. It might be the next slide. So our mass number, we said, in this case, was 29. That happens to be 29 protons and 29 neutrons, or the sum of those two. They really should have put in. So how many neutrons are there then? What we would do is solve for our problem. We have 29 equals protons plus neutrons. Do we know how many protons we have? Can we solve for our neutrons? Subtract 14 from both sides, and we now have the number of neutrons. Okay? Questions about that? Okay, let's see. Where's my slide? Not quite. So our periodic table, we can use that to figure out our atomic number and our mass number. You'll notice in this case, the example shown up on the slides, those numbers are centered above the symbol. They aren't shifted off to the sides like on our periodic tables up on the walls. Okay? We can still get that information regardless. You just have to make sure that you know where to look for it. Okay, the next big issue, yeah, I'll end with this. I think I'll end with this. Let's take a look at our atomic structure. I want to get into this definition a little bit. Electrons, we haven't quite developed what they are or what they mean as far as our structure goes, so we'll skip the electrons for the moment. What can you tell me about the protons? What do the protons tell you? What can you tell me if I have 2 protons? I have helium. What can you tell me if I have 47 protons? I have silver. What does the proton count tell you? Protons will define the element. Okay, we don't care about the electrons, but our proton count will define what element we're looking at. What happens with our neutrons? What do our neutrons define? Define our mass. Whoa, that's not an M, it's an E. Okay. What can we refer to different elements that have, or say the same element with different masses? We define the isotope. And that, almost guaranteed, is my next slide. Bing, there we go. So we'll talk about isotopes, neutron counts, all that fun stuff on Tuesday. And then we'll probably push into the first half of Chapter 5 and then probably double back to Chapter 4. I would guess we're going to get into the tail of Chapter 4 on Tuesday, just so you're aware.